for this particular problem, we're going to discuss how we can use these RICE tables in order to solve for our K values. And so RICE stands for reaction, your initial, change, and equilibrium. And so here you're basically kind of filling in a table so you can actually have some values that you can plug into your quotient equations in order to have something to solve for. And so one way or another, these problems are going to be written and so that there is going to be some way for you to solve for everything on this table. Not everything's going to be given to you. Sometimes you're going to have these problems where they're going to give you initial concentrations. Other times they'll give you equilibrium concentrations. Other times they'll just give you the actual values and you have to kind of do some manipulation to figure them out. So please note, this is one of the more simplistic versions of the RICE tables, but basically the same exact idea can be followed regardless of what values they give you and regardless of what values they're actually trying to search for. And so one thing you have to kind of pay attention to these particular problems, especially the one that I kind of wrote up here already, is once you are given the chemical reaction, that tells you a lot about how this stuff is going to change. And so first thing, hopefully you should all understand by now at least, is reactants change into products. And so in that case, your reactants have to disappear in order for products to appear. And so in these situations, when we talk about things changing, they change by reactants going away and products showing up. And so when we start writing out these values, and especially when it comes to the change, you have to make sure that your reactants are going to be going away, or you're illustrating this by subtracting stuff from your reactants. On the flip side, your products are showing up, so you have to kind of illustrate this by having a plus, or you're adding things from or going from your initial to your equilibrium. And so the other thing we have to kind of take, advantage of here is some, slightly more than high school level math. And in fact, it just has some X's that you have to kind of deal with. And so all of that to kind of tell you how these things are going to kind of come down here. So the first thing is, initially, I'm telling you that I have 0.5 molarity of A and 0.4 molarity of B, and I'm mixing these things together. And so initially, we have reactants. And so initially, it's like the fourth time I said it, we are going to have absolutely no products because, again, reactants change into products. There is no change yet, so you can't change yet. And so in these cases, most of the time, if you're given reactants, your products are going to be zero to at the initial start. So when it comes to change, as I mentioned at the very beginning of this video, this chemical reaction, the balanced chemical equation tells you how these things change. Using the value of X for our unknown, we know that our reactants are going to go away. And so for this, we can write out our minus 2X and our minus X. And I'm writing out minus 2X because two of these are going away at the same rate that one of those is going away. And so whenever two of those go away and one of those go away, on the product side, we have a C showing up and some D showing up as well. And so please note, these are going to be pluses because we are getting rid of reactants and forming products. And so at equilibrium is the sum of your initial plus your change. And so when we kind of go through and look at equilibrium on this side, we're going to have our 0.5 molarity minus 2x. I'm going to move this down a little bit so I don't smush everything. For our B, we have our 0.4 molarity minus x. And then on the side, again, for our C, it's very kind of simple to solve for because it is X. And the last thing we kind of go, I kind of moved that down too much now. And so, X, there we go. And so, last thing we have to kind of notice here is I give you an equilibrium concentration of D, or one of the products. And the reason why that's very important to us is because if you look at this, 0 plus X equals 0.2 molarity, meaning the fact that our X has to be 0.2 molarity. And so if we know that our X is equal to 0.2 molarity, because again, 0 plus X has to equal 0.2 because that was written there before all this purple stuff. And so for that instance, then we know the concentration of our C at equilibrium is 0.2 molarity. And so we can rewrite this here. let's move it over a little bit, 0.2 molarity. And so we also have an equation to kind of solve for our equilibrium for like B. We have 0.4 molarity minus X, which we just stated was 0.2. Kind of got erased a little bit there. But 0.4 minus 0.2, we have 0.2 molarity. And the last one for A, we have our 0.5 minus our 2x. And so 2x is going to be 2 times the 0.2 or 0.4. And so 0.5 minus 0.4 is going to give us 0.1 molarity. And so this may seem all simple and good, and you may be singing praises because you think you're finished, but we're still not there yet. And so after that, we still need to solve for our K. K's have not changed. K's, or the quotients at equilibrium, are still going to be set up the same way here. And so the K for this question can be set up with your products over reactants, or we have our C times our D, put all of this over our A, and make sure it's squared, times our B. And so here again, C, D, and our A has 2, or coefficient of 2, so we need to make sure to raise that to a power of 2. And then our B is going to be on the bottom just because it's still a reactant. After that, plug all the values in. And so here we have the values for all of these because we have everything that we need at equilibrium. And so C, we're going to be looking at 0.2 molarity. For our D, we're looking at 0.2 molarity. Put this over A and B, so our A is 0.1, but make sure that you have it squared. And then our B is our 0.2 molarity. Oh, sorry, I forgot molarity in my A. Molarity squared. And so here you have 0.2 times 0.2 divided by, in parentheses, 0.1 squared times 0.2. If you plug this into your calculator properly, I end up getting a K value, if it wants to write it out, of 20. And so what this is stating here is that 2A plus B very, very much wants to go in that other direction. This is going to happen at a pretty relatively nice quotient, and so it's going to kind of take a lot of things to kind of like push things back and forth.